So welcome back to the session again, and I welcome you once again, all of you. Eager to, we all are eager, ma'am, to listen to you. And over to you, ma'am.
Thank you. So first of all, are there any queries or we should proceed for georeferencing? Okay. Okay, is it visible? Is the screen visible?
Yes, ma'am.
Okay. So we have till now we have learned how to define the location of any real world feature. Now we said that in GIS what we actually need to do, we need to represent the different features on the surface of the earth within the GIS environment in form of layers. It may be a point, line or polygon feature. Okay, and we want to integrate, we want to overlay all these different layers. Okay, that is the problem we are talking about. The thing is that suppose I want to prepare the city map of Indore. Okay, there may be very different types of features. Some will be point features at the given scale, some will be line features, some will be polygon features. What I'll do, I will just I get a map of Indore and I scan that map. When I scan that map and I open that map in the GIS environment and I create points, lines and polygons based on that, the problem is that when you open, I'll just give me a second, I'll open this. When I open this map in GIS environment, it does not have any location information. Okay, we'll just see in the software itself. Okay. Ma'am has given me a map. I'll show that to you. I think you must have done this in your yesterday's exercise, how to open a raster. Okay. Now you can see that in this map, I have these coordinates. Okay. You will say, okay, we already have the location information here. I can always measure it from here and find out the coordinates of this particular point. So then just see here. I hope it is visible. As you must be seeing, you have some positive and negative values here. As I move my cursor here, okay, I'll take my cursor here. Here you have the coordinates written 75 degree, 18 minutes east longitude and 23 degrees, 6 minutes north latitude. But if you see here, you cannot see these coordinates here. So they are written, but they are not being read by the GIS. Okay. And where do these values come from? Just see, I take my cursor here. And as I take my cursor here, and you can see that the values are reducing. And somewhere here at the bottom corner, I must be having my 0, 0. Okay, so basically what you are seeing is the image coordinate system. What does image coordinate system mean? This screen, I will just remove this. This screen has its own coordinate system. Like the simple, you plot a X and Y axis on a graph. no? And where they intersect, you put the 0, 0. And then towards the east and the north, you put in the right, top right coordinate, in the northeast quadrant, you put both values as positive. In the northwest, the x values as positive and the y and the I'm sorry, the x values as negative and the y values as positive. In the southwest quadrant, you have both the values negative, and in the southeast quadrant, you have the x values as positive and the y values as negative. The same kind of coordinate system like you do have been doing in the graph is being used here by the system by default. Okay, so these values are that those values only. This entire space has its own coordinate system, but this coordinate system is not the actual coordinate system GCS or PCS, which you can see here written on the map. These values are not being read by GIS by itself. So now if I take my cursor anywhere here, okay, I cannot actually read the real world coordinate locations of Depalpur or Sevar or Hathod or Betma. Yes, I may just put my scale and then try to measure what latitude and longitude it is. But my software does not have this information that what is the real world coordinate location of Betma. So if you actually overlay some other layer which has in which Betma is there, that layer will not map on this map by itself because the location information is missing. So what I need to do is I need to attach this information which is written here. Now remember whatever I have told you in the first lecture. We have a latitudinal coordinate, a one coordinate and another coordinate. We have these two coordinate values, and in both these coordinate values are not just coordinates values. They have some projection, they have some datum, they have an implied definition of a spheroid or an ellipsoid. Okay, so these coordinate, I have to actually understand this and I have to attach that information to this map. And this simple task, what we'll be doing, is known as geo referencing. So, defined as fixing of locations of real world features within the spatial framework of a particular coordinate system. Now, please remember everything that I have told you about coordinate system in the last lecture. जब भी मैं कहूंगी coordinate system, all the concepts they automatically fall in. Okay, to establish a relationship between the page coordinates, the image coordinates you can say, on a planar map, those plus minus simple graphical coordinates and known real world coordinates. आपने क्या करना है? What you have to do is that you have to establish a relationship between, I take my cursor here, this has some 94 minus 1044 coordinate value, and it has some real world coordinate value which is 75 degree 18 minutes east and 22 degree 48 minutes north. So I have to establish a relationship. I have to establish a link between these page coordinates and these real world coordinate values so that for every single pixel in this map, my GIS is able to link both of them, and wherever I take my cursor, it is able to understand what real world coordinates are there for this particular point location. Okay, so I have to establish that link. Often involves conversion of map feature coordinates from image frame coordinates, row column, into projected coordinates, such as UTM coordinates. What we do in georeferencing, we convert our image coordinates into real world coordinates in a particular coordinate system. For this, what we do, we actually do coordinate transformation. Location of real world features fixed in one coordinate system can be transformed into another coordinate system. There may be that you have the location of real world features, either you do not have their coordinates, and even if you have, it may also be the second case, maybe they are in one particular coordinate system and you actually want them to be in some other coordinate system. You have your own data in one projection and you have actually acquire data from some other department which is in another projection. So but to actually overlay them, both of them should be in one particular coordinate system. So there may be two requirements: either it does not have any coordinate system at all and you want to assign a coordinate system to it, or it is in one particular coordinate system and you want to transform it into another coordinate system. Both of the things can be done through coordinate transformation. It is required when geospatial data are fixed using different coordinate systems, different map projections, or different datums. A manually digitized map, that the kind I have shown you just now, that is a manual digitized map. इसके अंदर now whatever you are seeing, it is the scanned image of a map, no? This map has been drawn and scanned. Now, whatever you are seeing here are page coordinates. Okay, they are in rows and columns. So it's the measurements are either in inches or DPI in case of a scanned image. If it is a satellite image, it is in row or columns. This cannot be used for analysis in a GIS project because ultimately in GIS, I want to make some measurements. I want to measure the distance. I want to measure the area. I want to make so many measurements. Then I want to align this particular layer with several other layers. Maybe I have this particular map of Indore, and then I want to I want to overlay the soil layer on it. I want to overlay the land use layer on it. I want to overlay the geomorphology of this region on it. I want to overlay the road network on that. So I want to overlay so many different types of information. So in my GIS project, I cannot overlay them unless they are referenced to one particular coordinate system. To make them usable, the map feature coordinates have to be transformed. So what I need to do is either I have to transform the page coordinates to a particular coordinate system, or I have to transform the coordinates from one coordinate system to another coordinate system. Whatever I do it using a set of control points. I call them CPs, control points, and I need a transformation equation. This process is known as geometric transformation. So what is geometric transformation? Geometric transformation uses a set of control points to establish a mathematical model that relates the map coordinates of one system to another, or image coordinates to map coordinates. It is as simple as that. What I'm saying is I want to have an equation. I can input the image coordinates and I should get the real world coordinates, where I can input the coordinates in one coordinate system and I can get the coordinates in the desired coordinate system. Okay, this process is known as geometric transformation. Maybe you can understand it like you all are professionals and must be looking for buying a land or a house somewhere. Okay, I say that the price of land is say 10,000 rupees per square feet. Okay, then if you want to buy a land, and I say that the land is maybe, I say 100 square feet. So it's a small figure, but let's see, 100 square feet. So you can immediately work out the price of the land. So what you actually need, you just need the per square feet rate of the land. Okay, then you have an equation. 10,000 rupees multiplied by size of the land, area of the land, and then you get the price of the land. Okay, as we say, if I say y is equal to 2x, you get put the value of x and you get the value of y. That is the simple concept which is applying here. I want an equation, that equation which can give me the real world coordinates or the coordinates in the desired coordinate system when I input the page coordinates or I input the coordinates in my source coordinate system. This entire this mathematical model which I use is known as my transformation equation, and this process is known as geometric transformation. So this geometric transformation, so what I want to do, I want to link my data to some particular coordinate system. This process is known as georeferencing. For georeferencing, what I am doing, I am building a mathematical model which is helping me achieve my objectives. That process is known as geometric transformation. When I carry out geometric transformation, it often involves what actually be done during this process. There may be differential scaling, rotating, warping of the image. Whenever I'm running geometric transformation, then it may happen that my input map or input data, input map may undergo change of scale. It may get rotated, it may get skewed, it may get shifted. Okay, as you can see here, this green one is my input map. When I run geometric transformation on this input map, I will get some output map. That output map may be like this cream one. Output map may be larger than the input map. Here also you can see in the x direction it has been enlarged less, and in the x direction it has been enlarged more. Enlargement or reduction means there has been a change in scale. So there has been a change in scale which is different in x direction and different in y direction. So I say that there has been differential scaling. Okay, then it may happen that my output map gets rotated. Okay, initially the direction between A and B, two places, was north-south, but in my output map, now the direction is northwest to southeast. So there is a rotation. It may get translated. From here in your image coordinate system, now after being transformed, it had shifted here. There has been a shift in X direction, there has been a shift in Y direction. Then it may get skewed. That means there may be a change in the angle. Initially in my input map, there was the angle between these two edges was 90 degrees. But after transformation, it is less than 90 degrees. Okay, so my output map may be different from the input data in variety of ways. Now just think that to get this output map, what I actually need to model in my equation, what I should have? I should have what will be the scale change in X direction, what will be the scale change in Y direction. Like with what it has to be multiplied, the original scale, it has to be multiplied by a coefficient to get the output scale in X direction, to get the output scale in Y direction. Then I must have a coefficient which tells me by what angle it has to be rotated. I should have a coefficient which tells me by what angle it has to be skewed. 1, 2, 3, 4. Then for modeling this shift, this translation, I need to have a coefficient which will tell me that it has to be shifted this much in X direction. It has to be shifted this much in Y direction. Okay, so I need to have at least 6 coefficients which will actually model these 6 types of changes. So here you just understand that when we run geometric transformation, there may be these 4 type of changes in my output map as be scaled differentially in the X and Y direction. It may undergo skewing, it may be rotated, it may be translated in X or Y direction. So I need an equation in which I have all these 6 types of coefficients which can model these 6 types of changes. There are several methods of geometric transformation. We will not go into all the methods today, but we will stick to one only, affine transformation. These different methods of geometric transformation, how do we differentiate between them? We differentiate them in, how are they different? They are different because different methods do not allow all these types of changes to be modeled. The coefficients which we are getting in different methods of affine transformation, different methods of geometric transformation. There are some methods which will only allow translation. There may be some methods which will only allow rotation. There are some methods which will only allow scale changes. But we need a method for georeferencing. I need a method which allows me all the 6 types of changes. Okay, so methods are distinguished by the geometric properties it can preserve. Based on that, we define different types of geometric transformation methods by the changes it allows. In what? Position, direction, scale, shape, and size. The general rules suggest, for purpose of georeferencing, the general rules suggest use of affine transformation. Okay, for both map to map or image to map transformation. What is image to map transformation? I have this map which does not have any coordinate information. I want to attach map coordinates to it. Or I have a map which already has some coordinate information, but I want in a different type of coordinate system. So I may need to do a map to map transformation. I may need to do an image to map transformation. For both these transformations, I need an equation which allows me all the 4 types of changes and which gives me all the 6 types of coefficients. And that type of transformation is affine transformation. So affine transformation, what does it allow me? It allows me to get a skewed output while preserving line parallelism of the object, input data. The affine transformation allows rotation. It allows rotating this is your input and this is your output. Okay, after georeferencing, affine transformation allows you rotation. That means it gives you this coefficient, by what angle it has to be rotated, in what direction. Then it allows you differential scaling. That means it will give you 2 coefficients. In your equation, you will have 2 coefficients. One will tell you what is the scale change in, by what coefficient you should, you will get the change in X direction, and by what in Y direction. Then translation, that means this will give you a coefficient which will tell you by what you have to shift your output to output coordinates in the X direction or Y direction. And then skew, how to, by what angle while maintaining the parallelism of the lines, it does not allow change in parallelism. Input में जो lines parallel हैं, they will be parallel in the output also. ये चीज it will not allow breaking the parallelism. So changes its shape to a parallelogram with a slanted direction. So it allows you all these 4 types of changes which are modeled by 6 types of coefficients. So a affine transformation is actually this type of a mathematical equation. Okay, need not go, all you all are engineers, much more in actually expert with mathematics than me. But here we just need to understand that we get these 6 coefficients in these equations. Okay, these are first order polynomial equations, and here you have A, B, C, D, E, and F. These are the 6 coefficients using which we can model the 4 type of changes. A is the coefficient for scale changes in x direction. E is the scale coefficient for y direction. B is the skew angle in degrees measured from the y-axis. If it has to be counterclockwise, it will be positive. It has to be clockwise, it will be negative. C is the translation in x direction. F is the translation in y direction. B is the rotation from x-axis, again positive if the rotation is counterclockwise, and negative if it is clockwise. So all these 6 coefficients, if I calculate these, somehow I get the values of these coefficients, then I can input the page coordinates and I can get the real world coordinates, which I am representing by capital X and capital Y. Okay, so for every input location, you have input coordinates, some x value, some y value. You input those input coordinates and you have these 6 values of these coefficients. Then by solving these equations, you can have for that particular point the output map coordinate, the output y coordinate, which is the map coordinate. So I hope this is clear. It is called as 6 parameter transformation because it involves 6 estimated coefficients. Now you all must be knowing, as I said, I'm not very good at mathematics, that to estimate this 6 coefficients, you need to have 6 equations. Okay. So with one pair of coordinates, I have 2 equations. So for 6 pair of coordinates, for 6 coefficients, I need to have 3 pair of input coordinates. Okay. So one pair of coordinates will give me 2 coefficients. So 3 pair of coordinates will give me 6 coefficients. Okay. So I need to have, what I want to do, I want to link the image coordinates with the map coordinates. तो मेरे पास कोई ऐसे 3 point हों. I should have any 3 such points for which I have the image coordinates and the map coordinates as well. Then only I will be able to solve the 6 equations for these 6 coefficients. Okay. So what I do, I have to search such points for which I can just get the image coordinates from my map, and I should be able to acquire the real world coordinates in a particular coordinate system for those very points. Such points for which you have both these types of coordinates are known as control points, because you have the ground real world coordinates for these points. You call them ground control points. Okay, so control points are locations of known coordinates of a physical feature. Control points are the locations of known coordinates of a physical feature that can be identified on the map as well as ground. Okay, control points are what? Just look at this. This is a satellite image or an aerial photograph, and here you can just see this T point in the road. You can very well identify this point here on the image, and also if you actually go to this place, you will be immediately able to identify this T point on the ground also. So what you can do is you can just take a GPS, go to the field, go to this T point and record its coordinates. Yes, remember those coordinates, if you are using a GPS, will be in geographical coordinate system on WGS 84 datum. Okay. So you can get the image coordinates from your just map. I just go here. I have my map here. I put my cursor here and I record the image coordinates from here. Then I go to the field. I'm sorry, this is a whole area. Just for example, I'm saying that you will go to the field, you will go to the same place and you will record the real world coordinates. And if you are using a GPS, then you must know that it is using WGS 84 datum and giving you the coordinates in geographical coordinate system. That means it is not projected data. Always remember that. Okay? So control points now so if I have three such control points, my work is done. Using those three sets of coordinates, X and Y, I can build this mathematical model, and using this model, I can estimate. If once I have the equation, then I can just get the real world coordinates for any pixel in my entire data set. So what do you call these points? You call them ground control points. Control points should be distributed over the area of interest. ये हमेशा हमें ध्यान रखना है. We have to remember that if you want to use three control points, these three control points should be scattered over the entire data. It should not be like that you are getting three, like you have a very good point, T point here, you have a very good point here also, and you have a very good point here also. So you will say, I'll take these 3 points. No. You should take one here, try to take here, somewhere here, try to take somewhere here. Whatever control points you are using, they should be scattered across the entire area. Otherwise, your whatever model you build and run, it will give good results in this area and will induce a lot of error in this area. Because always there will be some error. So that error will be compounded. So what we do is we try to actually capture the entire area using those limited number of points so that error is equally distributed and the overall error is minimized. An affine transformation requires a minimum of 3 control points to estimate the 6 coefficients. Lekin, we should also be conscious about the error. So instead of 3, we use 4 control points minimum. Minimum number of control points for an affine transformation is 3. But we use 4 because the 4th point gives us the error and we are actually able to make out whether our equation is giving us good results or not. So we will use 4 points. As soon as you input the 4th point, you will get the error. And if you will check if the error is too high, then you will try to take different new control points or those very control points again until the time you are satisfied that you are getting a good result. Then you will proceed for converting the coordinates of all the points in your data. So the control points for image to map transformation are called as ground control points. Now, as I said, there will be some kind of error. Okay, so how to make out this error? This error is known as root mean square error. I will just first explain you what does this error mean. How do we get this error? What you do is, if I say 2 multiplied by 3 is 6. Okay. If I say 2 multiplied by 3 is 6, then 6 multiplied by 3, 6 divided by 3 should give me 2. Is it right? If I multiply 2 by 3, 2 multiplied by 3, I get 6. If I again divide 6 by 3, I should get 2. It is as simple as that. अब इसको we'll apply this concept on the problem we are dealing with. I use 3 sets of control points. I build 6 equations. I calculate the values of 6 types of coefficients. For those 3 control points, I have the input coordinates, image coordinates also. I have the output map coordinates also. Therefore, I was able to calculate the 6 coefficients. What I did in those equations, if I input the image coordinates, I get the map coordinates. Using those equations, you have used those 3 core set of coordinates for building the mathematical model. Okay. Now what I do is, I test my model on the same 3 points. Okay. I input the real world coordinates in my equation and calculate the image coordinates. Okay. Yani, I have built the model using those 3 sets of coordinates. 3 sets of coordinates have one set of image coordinate xy, small xy, one set of real world map coordinate capital XY. Okay, 3 sets may be do set and one image coordinate and one map coordinate. And using those, I have built 3 equations. I have calculated the 6 coefficients. I have now these 2 equations with all the coefficient values. I use the same equations to again calculate the same coordinates which I have used for building the equation. Okay, so I input the map coordinates in the equation, that is the capital XY, and I compute the small xy. Then it should be like what I should get. I should get the same small xy, same image coordinates, but the problem is that does not happen. That does not happen. There is a shift between the input coordinate, input xy, and the computed. So if the input coordinate was, say, 2, 3, second row, third column, maybe, okay, 2, 3, then I should get 2, 3 back, but I don't get it. I will get, say, 2.4, 3.2, something like that. Okay, so there will be a shift between the computed and the actual source value of the coordinate. This shift will be there. How can I measure this shift? This has an xy, okay, xy value. This has again xy value. Suppose this is 2, this is 2.4, this is 3, this is this is suppose say 3, this is I must say 2.7 maybe. Okay, so there is a difference. That difference can be measured, of course, along the x-axis and along the y-axis. And if I want to measure this straight distance, I can always apply Pythagoras theorem. So I will square this residual, I will square this residual, and I will add both, and I'll put 10 under root, and I will get the value of this. This is known as RMS error. So RMS error is the distance between the input source GCP, source location of the GCP, and the computed location for the same GCP. And the equation which you employ, which you call the Pythagoras theorem, or and that you call a Euclidean, this straight line distance is known as Euclidean distance, and we call this equation Euclidean distance equation, and we call this shift, this deviation, we call it root mean square error. So I will say that the RMSE here is, if I say the RMSE is 1.5, then 1.5 means this 1.5 is pixel. So if I say the RMSE is 1.5, that means the distance is equivalent to 1.5 pixel. So if your pixel is say of 10 meters, then you can make out that the shift is around 15 meters. Okay, so this RMSE is always in the source coordinate system, that is the pixel width. Okay, so as you can see now, what does it actually, why it is so important? It is like you have now quantified the error. You know that if you run that equation which you have formed, then the coordinates will not be exactly the same as they should be. Then what we can do, we can just minimize the error. So because I am georeferencing a raster, it has a pixel. I am satisfied with the fact that my computed location must lie within the same pixel. I don't mind, but it should not go beyond that pixel. Okay, so if my error is less than half pixel, I am okay with it, because it will, when I actually complete my geometric transformation, the computed values will lie within the same pixel. Okay, I'm okay with it. They should not go outside the pixel. Then I will consider it as a shift. Okay, so I try that my RMSE should be less than 0.5. That means 0.5 pixel. If it is less than 0.5, then it will lie somewhere here only, and I am fine with it. If the error is more than 0.5, then my output pixel, instead of here, it will go somewhere here. There will be a shift in my data. So that is what I have to aim at. You get the RMSE for each control point also, and for the whole equation also, overall RMSE. Your overall RMSE should never be more than 0.5, and your per GCP RMSE should never be more than 1. It should always be less than 1. That is what the accuracy you have to aim at. Okay. So this georeferencing is a two-step process. Okay. First, what you do is, for your this is a frame. In this frame, we have, you can imagine that it is like a net, a mesh. Okay, जैसा जाली हम अपनी windows पे, doors पे लगाते हैं. So it is a kind of a mesh, and these pixels, these pixel values are filling this mesh. Okay, what we call these values, we call them intensity values, no? DN values, intensity values. So I can say that this raster, just for understanding, I'm saying that I can say that this raster is like a mesh in which there is a grid. Okay, and in that grid we have pixel values filled in. Georeferencing is a two-stage process. First, you project the mesh, then you fill in the pixel values. Okay. So, first, what you are doing is you have an input grid. You are using your mathematical model, whatever transformation equation you have designed, and using that equation for every input image coordinate, you calculate a map coordinate. Okay, so you have an output grid. Now for that output grid, the second problem with you is that I have an output grid now. Now I have to fill in the pixel values. When I fill in these pixel values, I again calculate, I run my equation backward. For each output coordinate, I calculate the input image coordinate so that I can make out that which pixel value has to be brought to this location. Okay, which pixel value from the input grid will be filled at this location. And remember, this is not a one-to-one process that you do. You don't just start from that the first value will be put here, second will be put here. No, you run the equation backward again. And I'll just no need to be like scared. You don't have to run it. The software does it, but we need to understand what goes on behind the screen. So what it does that it calculates the image coordinates for each output coordinate location. Okay, and whatever pixel value is here in this, the computed input coordinate location, it will bring it here. Okay? So this is the second step of georeferencing, that you interpolate the intensity values, or you can say we call it resampling. The first stage is that you project your grid, and the second is you resample, that is you bring intensity values and fill them in the output grid. So once the image is warped, once your output grid is ready according to a coordinate system, how do you assign DNs to the new pixel locations? Unfortunately, there is no one-to-one relationship between the movement of input pixel to output pixel value. What you do, you try to work out a value from the input pixel grid, which has to be shifted to this output location. But unfortunately, when you calculate this input value, it is not the same which you had input. Okay, so what to do? You have to calculate the value at this new computed location, and this process of calculating the value at the computed input location and shifting it to the output location, corresponding output location, is known as intensity interpolation. So the goal is to fill the matrix that is in a standard coordinate system with appropriate values from this input unprojected image or data. Since the grid of pixels in the source image does not match with the grid of the reference image, pixels have to be resampled so that new data files can be calculated and they can be put in the output image. This process involves extraction of values from a location in the input image. As you can see, this was my input grid where I had very clear row and column. I had values at the intersections of rows and columns. This intersection is 2, 2. This intersection is 3, 2. This is 2, 3. And this is 3, 3. And I had pixel values here. But when I actually tried to extract the value from this input grid, it told me that bring the value from 2.4, 2.7 location. Then I don't have any value here for 2.4 and 2.7. What to do? I will calculate that. And that all those methods by which I will calculate this are known as resampling methods. We have three main resampling methods. One is nearest neighbor, one is bilinear interpolation, and one is cubic convolution. Nearest neighbor method, nearest neighbor. Bring the value which is at minimum distance from the computed coordinate location. Which is the nearest? 15. So we will bring 15 here. Now the question comes that how did you calculate that this is the nearest? What we'll do is, just imagine that you prepare this triangle. You know that this distance is 0.4 and you know that this distance is 0.7. So 0.7 square plus 0.4 square and take a square root of this sum. Okay, 0.7 square plus 0.4 square. Take a sum of both the squared values and take a square root. You will get this. Okay, this is 0.4, this is 0.7, and you will get this distance, straight line distance. And then you calculate this straight line distance from all these 4 pixels, and you will see that this is the minimum distance. For this, we'll consider this triangle 0.4, 0.7. Yes, 0.7. I'm sorry, this will not be 0.7, it will be 0.3. This triangle, this will be 0.3, this will be 0.4, this will be 0.7, and this will be 0.4, this will be 0.6 and 0.7. And here it will be 0.6 and 0.3. So when you solve them, you will get 4 distances and you will just see which is the minimum distance, and you will bring this value, which is at the minimum distance from this position. You will bring this value here. You call this method nearest neighbor. In another method, what we do is we calculate a weighted average weighted by distance. A weighted distance weighted average of all these 4 pixel values. And put the weighted average here. In this method, we calculate a distance weighted average of 16 pixels, okay, around this location. Weighted average of all these 16 pixels, and you put it here. Now you will say, why do we need to do this? Why not we just go by the simplest method, which is the nearest neighbor? At times what happens when you do this, suppose here you have brought this 15. Then you proceeded to this. Which pixel value to put here? You got another point here. Again, 15 is the nearest neighbor. You put 15 here. Then for here, you get a value here. Again, you put 15 here. So at times what happens that when you use nearest neighbor method, a lot of pixels, they actually get the value from the same pixel value from the same location. So your output may be like patchy. It will have patches of the same pixel value. So at times this will not serve your purpose. So you will not have a smooth output. So for most of the cases, bilinear interpolation is a better method where you get the weighted average of all the 4 surrounding pixels. But then why don't we just leave nearest neighbor when it is not giving us good results? One good thing about nearest neighbor is that nearest neighbor is retaining the original pixel values. It is not changing the original information. Therefore, in bilinear interpolation, you are changing the original information, which is you are calculating the average of 4 pixels in cubic convolution, 16 pixels. So basically, when we work with satellite data, then we often use nearest neighbor, because actual pixel values is the actual information which the satellite has collected. So if we actually average that out, the original information is lost. Therefore, nearest neighbor resampling is normally used for satellite digital image processing, because we don't want to lose the original information. But when you are working with scanned maps or some other, if basically if the original information does not matter that much, but you want to have a smooth looking output, then you may use bilinear interpolation or cubic convolution. In the end, I will show you some books. You may note down those authors, and they are very simple books and not too expensive also. And for further details on these concepts, you may just go through those books. If you actually work using GIS, you will get all the merits and limitations and everything in the books. So here you just have to understand that if you want to have an attractive, a smooth looking output, then bilinear interpolation is good. Cubic convolution may also be good. But if you want to retain the original information, then you don't have an option, and you will always use nearest neighbor method. So this is the summary of whatever we have talked since morning. What you have to do for georeferencing: first of all, you need to identify the control points. Now the question arises, where do I go to find the control points? There may be several sources of control points. First, one of them I told you that you can go to the actual field and you can take a GPS and record the coordinates and come back. At times it is not possible to go to those places. Then what? Then you try to find some already georeferenced map of that area, and you can take the control points from that map. Try to take a high resolution satellite image already georeferenced, of which already has the map coordinate information, and then you can take the control points from there. Or, as I will show you, if you are using, if you want to, that is a very, I think I can say a very easy way of doing it, that you get a topo sheet of that area. And topo sheet always has the tick points. You have the control coordinate values written for the intersections. You can georeference the topo sheet, and then once you georeference the topo sheet, you will get the coordinates for each and every point in the topo sheet, and then you can identify features for which you want the coordinates, and then you can link your image or whatever data you are georeferencing to that topo sheet. Another way of doing it is, now that you have Google, so at times that also is quite helpful. You can take the coordinates from the Google, the Bhuvan maps, and a lot of platforms are now giving you maps with the coordinate information. So you can just go to Google, identify those points, and then take the coordinates. Whenever you are taking the coordinates from any other map or Bhuvan or Google or any such, then you must always know that those coordinates are in which coordinate system. What is the datum? What is the projection? What is the coordinate system of the source from which you are taking the map coordinates for the purpose of georeferencing? That is really very important. Like, when you are suppose everybody may not have access to the new topo sheets, but the old topo sheets are there in most of the departments and offices. So if suppose you are preparing some data for Indore, and you get the topo sheet of Indore, then you must know that you must first find out that what is the coordinate system, what is the datum, what is the actual geograph, whether the coordinates which are written on the topo sheet are in GCS or they are in PCS. You must know that first. Okay, don't just assume that they are in a particular coordinate system. As I will tell you, the old topo sheets of India were in the Everest, on Everest datum, and the values which are there written on the topo sheet, they are the geographical coordinates. Okay, so you must know that first. So whenever you get the map coordinates, then you must pay attention to the source coordinate system. Number one. Number two, which points to take as GCPs. As I said, first thing is that they should be such locations, such features which can be very easily identified on your map, whatever you want to georeference. And also they should be very, very clearly and accurately identifiable on the ground. Okay, so you can take building corners, you can take road intersections, you can take, suppose there is a bend in the road or in the suppose it's a canal, some kind of a permanent feature which has a clear geometrical shape, so that the corners or intersections can be identified. You cannot don't ever take the corners of a water body, a natural water body, or you can say a field. आप कहें मैंने खेत के कॉर्नर में खड़े होके ले लिया, that खेत may have shrunk or expanded, the soil may have it may have been extended a bit. Don't ever take any such location. I was standing there near the tree. No, don't take any such position location. Don't just stand anywhere here. Okay, I was standing here at the round. No, you will not be able to accurately identify the same point on your image. Okay, so always we will take such places like road intersections, road bends, canal bends, or house corners, building corners, such type of places. Don't ever take any such smooth bending, any point, or in the field, in the water body, natural water body, standing by the river, by the lake. No, don't take any such points. Number two. Number three, always try to capture the entire area. If you have to take 3 control points, then you have to take those 3, which they should be scattered over the entire area which is being covered by your image or map, whatever is there. If you so fourthly, these should be very, very scattered. Fifth, you should always proceed like take the first like here, and while you are that I'll show you when we do it actually, then I'll show you. So you'll always remember that these should be clearly identifiable on your map as well as on the ground. They should be permanent features. They should never be temporary features. They should not be natural features. Try to take, even if you are taking it along a lake, it should be a man-made lake with a clear pal and everything, so that you can identify that. You have to bear all this in mind while you are selecting the GCPs. Now, another question is how many GCPs to take. As I said, 3 are minimum required for first order affine transformation. But these are the minimum. Always try to take many GCPs. Even if minimum 3 are required, we always advise that go at least for 15 GCPs. Because it is very easy when you are georeferencing a topo sheet. But when you are georeferencing a satellite image, then you are not able to identify the GCPs on the ground very, very accurately. So there are some GCPs which have less error and some are there which have more error. So if you take more GCPs, there is a scope that you can eliminate those GCPs which have more error. So always we should try to take GCPs much more than what are minimum required for building the equation. So first of all, now how do we georeference? We have an input data. We get the GCPs, we get the image and the map coordinates for those GCPs. Then what we do, we update we link the image coordinates to their real world coordinates. How to do that? I'll just show you. Then we run the transformation on control points and we examine. That means we build the equation, mathematical model. We get some coefficients. Then in the background itself, the equation runs backward and then gives you the RMS error. If this RMS error is higher than the threshold, that means 0.5 for entire data set, all the GCPs together, and more than 1 for some particular GCP, then try to take that GCP again, remove that, take it again, take another GCP, whatever, but the error should not exceed the threshold. Every time you change the GCPs, you build the equation again and observe the error again. Once the error is within the limit, then you can proceed ahead. Then your equation is built, and then you apply this equation to the remaining all the pixels which are there in your data set, and you apply the transformation to all the features. And after you have done that, you get your output, and then you select the resampling method and you apply intensity interpolation also, and you get a outcome which is a new map which is based on the coordinate system which has been defined by you. So I'll just demonstrate. I have been given this map of Indore, and I will show you how to do that in Quantum GIS 3.16. This is Galti said it has been written 3.14. I will show you how to do it in Quantum GIS 3.16. So I think you all know that how to open Quantum GIS and how to open a raster data. So we proceed further from here only. This is like a topo sheet, you can say. You have a grid and you have the coordinates for the intersections of the grid, and you have some features here. Okay. Now, as I said, although because I already have these coordinates here, so I can use these points for georeferencing this map because I have clear real world coordinates. I am assuming that this data is in WGS84 datum. And as I said, always on the topo sheets, these values are written in geographical coordinate system. That means these coordinate values tell you that these are the positions on a spherical earth. Okay. So what I do is I go to raster because I'm going to georeference a raster. I will go to raster. From raster, I will select this georeferencer. Okay. Raster, georeferencer. When this georeferencer opens, I open raster. I go to where my data is lying and open it. Okay, so I have the map here. Now, what I have to do? First of all, I have to tell my GIS that what is the datum or something, whatever coordinate information of this input map. Okay, so I go to file, I go to raster properties. Okay, and I go to source. What I did, I went to raster properties. I go to source and I say, what is the input coordinate system? I say it is geographical coordinate system based on the datum WGS 84. Okay, what I have selected, this is a standard definition. Okay, this is a standard, you can say a code for the coordinate system, which is geographical coordinate system based on the datum WGS 84. So I go to layer properties and apply and OK. What I have done, I have told my GIS that whatever coordinates I will be entering, map coordinates for the GCPs I will be entering, you must understand that they have been measured in geographical coordinate system on WGS 84 data. That I have done. Okay, now the second step is I have to establish a link between my image coordinates for the GCPs and the map coordinates. So what I do is I go here, add point. You can also take it from here, edit, add point. Okay, add point. See, the cursor changes to a crosshair. I go here, I zoom it a bit. Okay, I take this and I click here. Okay, in the center. As soon as I click that, I get this window. Okay, and then I enter it here. As soon as I have clicked, it has taken the image coordinates. Now I have to input the map coordinates. What are the map coordinates? X is 70, I'm sorry. Yeah, X is longitude 75, 18, 0. What are you doing? It is written here. Do read this very carefully. Okay. And what you have to do? You are entering the values in degree, minutes and seconds, and you have to put a space after each. Degree space, minutes space, and second space. Here I put the latitude 23 space 6 space 3. Okay. See, you have the image coordinates here and the map coordinates which you entered are here in converted into degree decimal. It automatically does that. Now, as I said, I should mark the GCPs scattered over the entire map. And the sequence which you will take is also, you will first take a GCP here, then the second GCP far off from the first. So I'll take this one. Okay. So I put again, I'll just do it not very accurately. Again, 76 space 12 space 0. 22 space 12 space 0. Okay. I'll just take it like that. You can do it later in hands-on. You can take it quite carefully. I have taken these three. Okay, and these three are enough for building the equation. But I just want to see how accurate my GCPs are. So I want to calculate the error also. So I will take the fourth GCP. As soon as I take the fourth GCP, it will run the backward equation and give you the error. So 75, 15, 0, 22, 12, 0. Okay, So you have all the 4 GCPs. Now you will go to settings and you will tell GIS what kind of equation is to be run. Okay. So I say that's run first order polynomial. This is the affine transformation, first order. Resampling method you may keep as nearest neighbor, which is the target coordinate system. I will keep it this only, EPSG 4326, which was the source coordinate system. You can have a different also. I'm not taking that. And you define the location where the output is to be saved. I say put it in my folder. Okay. You can also save these GCP points so that if you have to close your work in between and open again, then your entire work is not lost. It is a simple map, but when we work with a satellite image, it takes a lot of time to identify the GCPs. And then it is like you take too many GCPs, so it's always better to save the file. And then you say that load in the software when you have completed this thing. Okay. As soon as I have defined the equation, I get the error here. And you can see that the error is well within the limit. It is 0.43, less than 0.5 on all the GCPs. So I'm happy, my equation is good. I will go and then say start georeferencing. Now what we have done and what needs to be done further? First, I opened my raster. I told the GIS that what will be the coordinate system of the values which I will be entering. Then I identified the GCPs and I input the image as well as the map coordinates for those GCPs. Then I defined the equation. Now, when I have defined the equation, then the equation has till now it has worked on the 4 GCPs only. But now if I'm happy with the equation, then I need to apply that equation on the remaining pixels also. So I will say start georeferencing. It says georeferencing successful. Raster has been successfully georeferenced. Okay, I minimize this and I open my georeferenced map and now see here. Instead of the map coordinates, image coordinates, you are getting the map coordinates in latitude, longitude, degree, decimal. If you're not happy with degree decimal, go to project properties, go to general, and here coordinate display, take degree, minute, second, or degree, minutes would be fine. Apply. Okay. You have now the coordinates in degree, minute, second. Degree, minute, sorry. Okay. So now I take my cursor to Depalpur, and I have the coordinates of Depalpur. I take it to Hathod, I get the coordinates for each and every single pixel. I have the coordinate information. So this is geo referenced data. Okay. So this is all. So this is all about georeferencing and how to do it in Quantum GIS. Any queries?
Thank you very much, ma'am. Very impressive and very insightful presentation. Any queries?
Ma'am, for a satellite image also, do we follow the same?
Yeah, yes. For the satellite also, you'll be
Ma'am, can we
following the
do some
same.
hands-on actually? Actually, this is the first time when we are
Hands-on,
listening now. So we are missing it out actually. Many things that you have said, when we are trying to apply it and we miss it out. Means
yeah, actually,
this.
I think lunch you have in hands-on session on georeferencing.
The same.
Chore will be taking that.
Okay.
You'll be doing it. You'll be doing the hands-on in the post-lunch session. If you want, I can give a demo again if you want to understand that. But hands-on he'll be doing with you. Huh? You just understand the concept now. So what you have to, the thing is that it is as simple as that. You have the image coordinates. You want to convert them into map coordinates. First, you have to tell GIS that what is the coordinate system, which is the coordinate system in which you will be inputting the map coordinates of the GCPs. First thing. Secondly, you identify your GCPs. You tell the GIS that these are my GCPs. These are the image coordinates of my GCPs. These are the map coordinates of my GCPs. Then you tell it that which kind of equation is to be modeled. So you have selected, then you tell it that which is the coordinate system in which I want my output. Then you run the georeferencer. First, the equation is designed, or it is built for only the 4 GCPs that you have given. And once you are happy with the error, then you apply the equation to the remaining pixels also. Yes, that is the process which is to be followed. Okay. Now the thing is, you should know what is the coordinate system of your source GCPs. As I said, आपने जैसा कहा कि ना, we can suppose you take the GCPs from the Google, the map coordinates from the Google. Then you must first find out what is the coordinate system which is being used by Google. If you are taking the GCPs from a topo sheet, you must first find out what is the coordinate system of the topo sheet. So that is very, very important. Okay. And right now, ma'am, as you said, for the satellite images also, you need to, this is the procedure, this is the fundamental procedure which is followed. For the satellite images, at times we need to georeference for 2 purposes. One is the image registration. That is you have a satellite image which does not have any kind of map coordinates with it, and you have to georeference it afresh. Then usually what we do is either we take the coordinates from the Google or we take the coordinates from another map. So that is you can acquire, or you go to the field and get it through the GCPs. Another thing is that you have to overlay 2 satellite images of the same area. Okay, both of them are georeferenced, but they may be in different coordinate systems. This is known as co-registration. अभी आप लोग GIS पढ़ रहे हो, you are not studying image processing, but in image processing at times I have to overlay multiple data sets of different satellites, say. Then I have to co-register those layers. That is, I have a parent satellite image. I have another satellite image which may already be georeferenced but may have a different coordinate system. I have to register the child image to the parent image. That is known as co-registration. But the process will be the same. The source coordinate system, identify the GCPs, you input the GCPs, see the error, run the equation, and georeference. ये steps हर में रहेंगे.
Thank you, ma'am.
I want to add something, ma'am. We'll be uploading all the recordings to our YouTube channel of the college. So all the participants will be, they will be able to access that through the link provided. So I think that will be very helpful to you, Abhishek.
Yeah.
Okay.
Okay, and regarding doing anything in quantum GIS, you must all have heard of Ujjwal Gandhi. I think Chauri sir must have mentioned, otherwise you could ask him. and he is a very passionate GIS person who has written tutorials for each and every tool you have in GIS. Okay, so data is also there. Initially, his website was spatialthoughts.com, and I think it is still there with the same name. Otherwise, you can just Google Ujjwal Gandhi Quantum GIS tutorials, and all the tutorials with snapshots of all the steps along with the data are there. So you just need to, I'll just show you the books. I'm sorry. Just once more, I'll share the screen so that it comes in your recording also. Yeah. These are some books that you can go through for theoretical understanding. This is a very good book, Katie Chang. It is primarily based on ArcGIS, but the concepts are the same. And it has 12 chapters. And if you go to these 12 chapters, very short chapters, not too long also, and you can very easily understand all the basics of GIS. Then we have MN Demiers again, and all these books are very cheap. 500 to 600, and I think even less, and are available on all the platforms. Ian Haywood and Lo. This is a bit detailed. Once you have the basic understanding of GIS, then you can also go through Low and Jung. And P.A. Burrow and McDonnell again is a very good book. But to start with, I always recommend these books for the basic concepts. ताकि शुरू में डर नहीं लगे, and you can just proceed slowly and slowly. So basic understanding, these books are very, very good. All are available, and I think they must be available in the libraries also. So you could go through these books for basic concepts. And regarding the practical part, you can always go through the tutorials written by Ujjwal Gandhi. They are really the best. So I think I should take your leave now.
Yes, ma'am. Thank you so much. It was very lucid. Means you explained it very nicely. Means it is on the flow. Thank you.
Thank you so much, ma'am. It was neatly presented and we learned a lot. And thank you for the references also, ma'am. Thank you so much.
Thanks to you for listening so patiently for so long time.
Ma'am, can you share the presentation with Aradhana ma'am so that ma'am can share it with us? So that would also be, we could use it as a reference actually.
Yeah, I don't mind. I'll share the presentation, but right now I have to rush to my university. So Aradhana ji, if I forget to, please drop me a message and share the presentation with you.
Yes, sure, ma'am.
Thank you.
Thank you very much, ma'am. Madam, you actually explained in a very simple and very interesting way, I must say. Like besides telling the basics and procedures, you also mentioned the do's and don'ts, what to do and what not to do. So it was like icing on the cake. And I appreciate, sir, ma'am, your efforts. And thank you very much for being with us. Thank you. Thanks a lot.
Thanks to you.
So all the dear participants, we will break for the lunch, and we'll start at 2 p.m. sharp. Okay?
Okay, ma'am.
Yes, ma'am. Ma'am, will you be sharing right now the attendance sheet?